another distance learning notes. Today we're going to talk about calculations with weak acids and weak bases. Not new, we've been talking about weak acids and weak bases, or weak and strong. So right now, why don't you stop the video and think about what makes a weak acid weak and what makes a strong acid strong. Stop now. All right, welcome back. Well, hopefully you recognize that a weak acid will only partially dissociate and a strong acid completely dissociates 100%. Here we go. So our essential question today is, how do you calculate the pH from the concentration of a weak acid or base? Calculations with weak acids. There we go. All right, reminder, again, this is really important. Dissociate partially. That means when I take a weak acid like acetic acid, vinegar, and I put it into water, it will dissociate, but not 100%. So I don't really know at that point what the concentration of hydrogen is in that solution. So we have to do some things to figure that out. So only some of the hydrogen ions are released into solution. This is important. The concentration of acid does not equal the concentration of hydrogen ion for a weak acid. This is true. For a strong acid, they do equal. So again, one more time, weak acid does not equal the concentration of hydrogen ion in solution. They're not going to be the same concentrations. You will need to use an equilibrium constant to determine the hydrogen ion. So we're going to be figuring out how to calculate a K, our equilibrium constant. This is a great graphic down here. It's one of my favorites. Again, the idea here is, as you look, I don't know if you can read this, but it says strong acid. And it shows my acid here. And it's got green and white. And you can see all those acid molecules are all together. But when I put them in water, the acid dissociates. So the green and white circles, all of them, 100% dissociation. Here we have a weak acid. And so here's our weak acid. Looks like our strong acid at the beginning, right? All the acid molecules, this time it's purple and white, so all these molecules are together. But when I put them in water, this is the difference between a strong acid and a weak acid. And that is, see, there's only one molecule that's actually dissociated. The rest are all still together. So again, the concentration of the acid does not necessarily equal the concentration of the hydrogen ion. To where over here with a strong acid, those two concentrations are the same because all the molecules dissociate. Important concept there. Okay, let's get going. So using an equilibrium constant. So equilibrium constants have the same general formula. And what is the formula? K. We use a large letter K to represent our equilibrium constant. And it is the products, now brackets are around it, so we would read this, the concentration of the products divided by the concentration of our reactants. Note that the concentration of the reactants and the concentration of the products is the concentration after the acid has partially dissociated. For any acid, the equation for dissociation is HA goes to H plus and A minus. This is a general form for a weak acid. So therefore, we're going to take the concentration of our products, so we put brackets around H plus, brackets around our ion there, divided by the concentration of our acid. This is how we will calculate our equilibrium constant. All right, well, let's try a problem. So we have example 13-12. It says, suppose you have a 1 molar solution of acetic acid. What is the hydrogen ion concentration after it dissociates? Well, as with any problem, you want to look at what it is you have been given. So we have been given 1 molar acetic acid. Now you want to stop here. What kind of acid is acetic acid? Is it a strong acid or is it a weak acid? All right, hopefully you recognize, because you've memorized those 6 strong acids, that acetic acid is weak. And that means that we know that the concentration of our acid does not equal the concentration of our hydrogen ion. We want to know what is the hydrogen ion. So we're going to start at an equation. So this is our generic. So instead of HA, we would have acetic acid, H plus, and the acetate ion. You're going to create an ICE table. Now, ICE is an acronym. It is the initial concentration, the change in concentration, and what's the concentration at equilibrium, or what we call our final concentration. So initially, when this reaction starts, if I have 1 molar of this acid, right, that's what I have, 1 moles per liter, that means I don't have any product, right? Reaction hasn't started yet. All right, change. Now, we don't know what the change is, so we're going to use a variable. But what do we know? We know that this concentration, is it going to stay? Is it going to get bigger? Is it going to get smaller? Is it going to stay the same? The answer is it is going to get smaller. So we're going to say, all right, it's going to go down by X. While this goes down by X, these two, notice they have positive. That means they're going to go up by X. And then lastly, we're going to establish, well, what's that going to look like when we reach equilibrium? And the answer is you're going to have 1 minus what reacts, and then these two will be our concentrations, how they went up as a result. So this is an ICE table, and it's very helpful in calculating equilibrium expressions in situations where we're dealing, again, with weak acids and weak bases. All right, let me get rid of this here. Remember that weak acids only dissociate partially. Since we don't know how much, we use X to represent the portion of the original acid that dissociates. All right, so that's just kind of going over what we just said. This is going to represent the concentration when the reaction reaches equilibrium. So we know it's going to go down by X. And again, these are going to be what the concentration is after the reaction reaches equilibrium. So they're going to go up by X. How to calculate equilibrium using, or how to calculate using equilibrium constants. So here we go, we have our ice box. And now we're going to write our equilibrium expression. So K equals the products over the reactants. And again, I'm not going to get into that. All right, refer to your ICE table and insert your equilibrium final concentration. So we go back to our ICE table. Let's just look at this. So right here. So this is the information that's going to go into your equilibrium expression right here. Okay? So these are my reactants. These two are my products. So now moving forward. All right, that's where we're here. So you can see I have concentration of X times the concentration of X over 1.00 molar minus X. All right, let's see. So we're going to look up the equilibrium constant. So we need to know what is the K for acetic acid. So for that, it's a reference material. So we're going to look at a reference table for some dissociation constants for weak acids. Here is our acetic acid, and we can see that it is 1.8 times 10 to the minus 5. So we're going to put that in here. And now we have to deal with solving. Simplify the amount of weak acid that dissociates. Simplify. The amount of weak acid that dissociates is much, much smaller than the original concentration, so we can ignore it. All right, take a look here. Do you see this X? Because this is a weak acid, and we know it only partially dissociates, that amount is so small that we say it's almost negligible. And we're going to take a liberty, right? And the liberty says this guy is so small, we're going to say that it's really not going to change this concentration by much. And look down here at the bottom. We have basically dropped the X, but be careful. We want to make an assumption. I would say you have to put off to the side, assume that X is much, much smaller than the concentration of our acid, right? Because in math, we don't just drop variables, right? That's illegal. But if we can justify it by saying, listen, this guy's so small, it's not really going to matter. And we want to do that. I mean, If we keep it here, we're going to have to use the quadratic equation. By taking this, because it is so small, we have much easier math for us to do. So 1, it's so small, it's very negligible, and 2, it's going to make our math lives easier. But IG required, you want to make sure that you give some kind of a notification that you recognize that this is so small, it's not going to affect it. So you can drop that X. All right, now we can get to solving. So there you go. So X times X is X squared over 1. And you're going to rearrange the equation to solve for X. So we're going to multiply 1 by both sides. So now we have 1.8 times 10 to the minus 5 equals X squared. And we're going to square both sides. And X will equal 4.2 times 10 to the minus 3. Remember, what does X equal? X equals, actually it equals, well, let me go to, it equals a hydrogen ion concentration. All right, I want to go back. Let me go back this way. Okay, so remember, this is X. So whatever that answer is, right? X equals the hydrogen ion concentration. It also equals the acetate ion concentration. And then we can plug in 1 minus X and we can actually find out what the concentration of the actual acid is as well. But we have to go back to the question. The question wanted to know, what is the hydrogen ion concentration? That's why we're just going to go ahead and go, all right, now we know that X is our hydrogen ion. We can box it out and we're done. All right, here are some practice problems for you to do. All right, example number 1313. I'm doing 2. Suppose you have 3.41 molar solution of lactic acid. What is the pH after it dissociates? Assume that it's a monoprotic acid. Again, thinking about what's been given. We go 3.41 molar, and then we go lactic acid. Is lactic acid a strong or weak acid? Is it one of the 6 you're supposed to know? The question is, what is the pH after it dissociates? Well, if you recognize that it's a weak acid, then you know that we can't assume that this concentration and the concentration of H plus are the same. If it were, we'd have a real easy problem. Plug it into the definition of pH. But it's not. So in order for us to do this, we're going to do an ice table. Let's see here. So again, you have to write the equation. What is the equation that's happening? So the dissociation of the acid, and again, we're just using a general format. That's absolutely fine. This works. The problem tells us it's monoprotic, so it only has 1 hydrogen. Yay. Create your ice table. So initial concentration, change, and equilibrium. The concentration initially is 3.41. The concentration of our products, 0. We haven't started this reaction. We know when this reaction begins that it's going to go down. This concentrated lactic acid is going to go down by X. While this goes down, these 2 concentrations are going to go up by X. We're going to use this to get our concentration at equilibrium. So this is going to be 3.41 minus X. This will be X, and this will be X. We need this information to plug it into our equilibrium expression. We're going to write the expression for the dissociation constant. Stop the video and practice writing the expression. K equals, go. All right, hopefully you said K equals the products over the reactants. The products are the concentration of H plus times the concentration of A minus divided by the concentration of HA. Now that we have that, we're going to refer back to our ice table on the equilibrium, that 3rd column, and we're going to plug in that information. So our products are X, and our reactants are 3.41 minus X. Remember, what do we know about this X? What do we know about that X? Well, we know that it is so small. that it's almost negligible. It's not going to change this concentration very much. And we're going to take a liberty. All right, and the liberty is, look what happened. There's my x. There's no x. Let's do that again. There's my x. There's no x. What's going on? Again, we're going to assume that x is so small that it's negligible, and we're gonna take it out of there, and that's going to do it. It's going to make our math a little bit easier. And now we can solve for x right here. So we're going to multiply both sides by 3.41. So now we have that, and it's going to equal our x squared. We're going to take the square root of both sides. So now we have x equals the square root of all of that. And now we have x equals 2.1849 times 10 to the minus 2. Therefore, again, what do we want from this? What was the problem? We want to go back and look at that problem. What am I trying to do? We know now that the hydrogen ion concentration is 2.1849 times 10 to the minus 2 molar. We have not done final rounding for significant figures because we're not done yet. We haven't answered the question. The question was, what is the pH? So now that we have the hydrogen ion concentration, we can calculate the pH. And the pH is 1.7. And it's rounded to 2 significant figures because the Ka only had 2 sig figs in it. Right? Yay. And there are your practice problems, so make sure to practice these problems. It's important.